Again, thanks everybody for attending today. We'll get started in another couple minutes. Still got people rolling in. Welcome everybody. I think we'll give it one more minute because it looks like people are still coming in. It's kind of like making popcorn in the microwave. You know, you're supposed to wait until the pops slow down and sort of stop. When people come in, there's like a little beep beep. When a lot of them are coming in, you get a lot of beeps. Then it slows down. I think maybe it slowed down. Okay. And it's 11:03 Central Time. Okay, we'll go ahead and get started then. Uh, Here's your official welcome. Welcome. I'm Mike Riddle. I'm president of VinCab America. And for what it's worth, an engineer by education and a long time in our industry. It's now pushing 30 years. Makes me feel old. In any event, today's topic is OPGW Engineering 101. We're going to be talking about design factors and best practices, very basic cable concepts for OPGW. This webinar is RCEP compliant. That's the Registered Continuing Education Program. We've met their standards, and that means that if you want, you can get an hour of professional development credit. The way that you do that, we'll explain at the end. Alexis, please remind me to explain at the end. And you'll get like a certificate. So the hours come through them. They have like a web portal for that. This does not mean that they endorse any of today's content. It just means that we've met their standards to offer the credit. So we begin with a purpose statement. So we're going to talk about the advantages and disadvantages of the three basic design types of OPGW that are used today. We'll talk about the best practices for each type. And we're going to talk about some design considerations, the trade-offs and the trade-offs between them, your fiber count, your diameter, your fault current capacity. We'll then look at some details about how you calculate fault current capacity, and then how it's computed by a cable manufacturer. And then we'll finish by touching on some basics of lightning performance. So here are the specific learning objectives, and I'll just give you a moment to quickly review those. Okay, and we'll keep moving. So rules for today. So we've already done the introduction and sound check. The presentation itself is going to last about 50 minutes. Then we'll open it up for questions, which can be done via chat, or maybe we'll figure out how to let you go live. We'll see. We'll work something out. The question should be related to the topic, so no business related stuff. And, I'm happy to stay on as long as people have questions. If it goes over, it goes over. And of course, you're welcome to drop out after the presentation is over. Although, yeah, hang on, for how to get your credits if you want your credits. All right, so let's get started. So OPGW is optical ground wire. The governing standards today are IEEE 1138, the 2001 edition, the 2021 edition. That edition replaced the 2009 version, which had been in force for quite a long time. IEC as a standard, 60794-4-10. What you find is that the IEEE standard is used in the United States and some countries around the world, and if they don't use the IEEE, they use the IEC. And I just want to remind everybody that the primary function of an OPGW is to replace a conventional shield wire or ground wire. The terms are synonymous. They're just emphasizing a different function of that conventional shield wire or ground wire. When you say a shield wire, you're talking about a cable, or you're emphasizing the function of protecting the phase conductors from lightning. And if you use the term ground wire, you're emphasizing the function of the cable acting as a path for fault current, but same cable, two functions. OPGW added a secondary function in the form of optical fibers for data and communication. And like a lot of things in life, it started off as a secondary function, but today the secondary function is probably just as important, maybe even more important in some cases than the original primary function. That's just how things work in life sometimes. So we're going to start by reviewing some basics about fiber and tubes. These concepts apply regardless of the type of cable, that is, whether it's OPGW or ADSS or something else. They're important, fundamental, you might say. First up is the fiber. The overwhelmingly most commonly used type of fiber today is what's called low water peak single mode fiber. Forgot to spell out single mode. The international standard that governs that is ITU-T G.652 Table D. An example of this is Corning's SMF-28 family of fiber, but there are others that are this same basic fiber. OFS, for example, has their all-wave series, and there are other companies that have standard low water peak single mode fiber. It's kind of your vanilla fiber. An important thing about that type of fiber is that it's generally splice compatible. So you can splice the Corning SMF-28 is currently SMF-28 Ultra is currently Corning's sort of flagship fiber in this category, and you can splice it directly to OFS all wave, and they're going to work fine. Corning is going to have their reasons why they think their fiber is a little bit better than OFS, and OFS is going to have their reasons why they think their fiber is a little bit better. Me as a cable vendor, I can tell you that they're both good. And again, the big takeaway from this is the fact that they're splice compatible, so you could use them together in the field. Standard single mode fiber is good for about 60 to 90 miles. After that, you need to basically retransmit the single. I'll just mention in passing the other type of fiber that you commonly see, not commonly, occasionally see, and that's non-zero dispersion shifted fiber. That has a different standard, and the two best known examples of this type of fiber are Corning Leaf, which stands for Large Effective Area Fiber, and OFS True Wave. These are not splice compatible. It's because they're correcting for a problem in fiber but they do it in slightly different ways. So not such a good idea to splice these directly together. I won't go into detail about that today in the interest of time. These allow you to go much greater distances, up to about 250 miles, or you can boost your bandwidth using dense wavelength division multiplexing, DWDM. So you see this type of fiber sometimes used like out in the West for going very long distances, or in the Northeast of the United States where you need the higher bandwidth because of the more dense population that some utilities are trying to support, uh, and lease the fiber to telecommunications service providers who need that higher bandwidth. So today, that's enough said about that. Again, big takeaway, the low water peak single mode fiber is still the most commonly used fiber type. There are other fibers out there, multi-mode. We make a reel of OPGW with multi-mode in it about maybe once a year or so, maybe less, maybe once every 2 years or so. Not very common. There are other fiber types. There's G654 fiber, and for years people have thought that that would replace the standard single mode fiber, but so far that hasn't really happened. For now, just remember these two, and of these two, the overwhelmingly most important one is the standard low water peak single mode fiber. Fiber has its own specifications. Lots of performance factors and its own elements. And in fact, we do an entire webinar just on fiber, the basics of fiber. For now, I'm just going to talk about the single most important performance specification with fiber, and that's attenuation. Attenuation is the loss of power over distance. It's generally expressed in dB per kilometer, but it could be any unit of length. So decibels is a unit of loss, and then you have a unit of length. But so it could be dB per miles or dB per feet or dB per furlong if you really wanted to. Here in the United States, you do sometimes see dB per 1,000 feet. That's actually really used. Um, but the point is that it's loss over distance. And what that means is that at the beginning of the cable, you've injected a certain amount of power, so your signal has a certain amount of power with it, but over distance, you've lost power. So the signal at the output is lower. Chromatic dispersion is another important fiber performance specification, but we're not going to talk about that today. Let's talk about attenuation. So if it's important, then you ought to have some way of measuring it, which you do, called an optical time domain reflectometer, or OTDR. And then you ought to have some requirements around how you measure it. And let's talk about those. So you should have attenuation limits. So that's the maximum loss or the maximum attenuation that you're going to allow. And I would suggest to you that you should be looking at maximum loss for each and every fiber after cabling. So let's talk about what that means. First, the limits should apply to each and every fiber. That's what I mean by individual here. Maximum, I think, is somewhat self-explanatory. The loss should not be any higher than whatever the limit you've set. So then individual is each and every fiber as opposed to averaging across a reel. Some cable suppliers do try to get you to do that. You as the user, there is no benefit for you for that. None. Not even a little bit. Except maybe you make that supplier happy who wanted you to do that. But really, with today's manufacturing, if you buy a 48 fiber cable and you want the limit to be X, there is no reason why all 48 fibers cannot meet X. Basically, you're giving a cable supplier an out if you allow them to average the limits. And potentially you're setting yourself up for the situation where you specified and purchased a 48 fiber cable, but one fiber has attenuation that's high and may be high enough to where it's effectively not useful for you, but the average for the reel could still be okay. So why do that? Like I say, I see no benefit for a user, and I think any good company, any good cable supplier would agree that each and every fiber will meet the limit. And if you insist, hold your ground, maybe some suppliers will complain, but the truth is that they can meet this if you hold your ground. The limit should apply to the finished cable versus the bare fiber specifications. You can get a spec sheet from Corning and OFS and any other supplier, and out their factory door, the fiber is going to have a certain attenuation characteristics. But when a cable company takes that fiber, they have to handle it. Typically, they have to do coloring. Certainly, they have to put it into a tube of some sort, and then that tube has to be taken and put into a cable. So you've typically got 3 processes. Often you have more. And each time you handle that fiber, you could be increasing the attenuation just a little bit. But if you make specifications based upon the bare fiber, what could happen is that a supplier can tell you, yeah, we bought the Corning fiber and it fully met your specifications. But after we processed it, now it's got higher attenuation, and hey, it is what it is because you specified bare fiber, not finished cable. So again, no benefit to you to specify only bare fiber limits. There is a potential downside for you. Therefore, you should specify what you think are good limits or what limits you need. The common measurement, I already talked about dB per kilometer. The wavelengths that are commonly used for measurement are 1310 and 1550. If you're using 1625, you might want to know that as well. But generally, if a fiber is good at, well, really the benchmark wavelength is 1550. But in general, if a fiber is good at a higher wavelength, it's also good at the lower ones. But the reverse is not true. So a fiber could be good at 1310, but not good at 1550 or 1625. Fiber gets more bend sensitive as the wavelength increases, and that's why it tends to be goodness rolls downhill, but goodness does not roll uphill, so to speak. And really, your benchmark is 1550. It's kind of the workhorse wavelength anyway. But not bad to measure at 1625. And if you're measuring at 1550, you can also measure at 1310. So, you might as well know those figures. So let's jump back up because I kind of skipped over bidirectional. Bidirectional means you're measuring from the outside end of the cable and the inside end of the cable and then averaging the results. I'm a lot old school, and I think that's the best way to do it. And for OPGW, that is still my recommendation for doing it. Dielectric cables, the industry has shifted more to doing outside in testing only for practical reasons. The practical reasons are that dielectric cables, A, tend to have higher fiber counts, and B, they are produced in much higher volumes. So a typical OPGW strander is going to run around 5 meters a minute, maybe more, maybe a little less. Depends on the strander type. But usually you're dropping a reel a day on a stranding line, roughly per stranding line. A dielectric line, an extrusion line is going to run about a factor of 10 faster. So for every 1 OPGW reel you produce, you're likely producing 10. And so that kind of overwhelms your testing capability. That's why the cable manufacturers have migrated towards outside in testing, especially for dielectric cables. But as I said, I'm old school for OPGW. I think you can sustain the bidirectional testing and averaging. What limits should you use? Well, for the standard single mode fiber, 0.34 dB per kilometer at 1310, 0.20 dB per kilometer at 1550, and if you're measuring 1625, 0.22 is a good value to use. These are good values for that finished cable measurement that I talked about. So it's allowed a little bit of increase during processing and handling, but a cable supplier's got to be doing a good job to meet these limits. And then if you're using that non-zero dispersion shifted fiber, for technical reasons I won't go into, 1350 is not measured or specified. So the limits for 1550 would be 0.22 and 0.24. I mentioned already that there are other fiber types that are available, but these are kind of in the category. If it comes up, give me a call and we can talk about it and I'll help you deal with it. So we've talked about the fiber, and I mentioned already, first you color fiber, then you put it in a tube. So let's talk about those tubes. For aerial cables, the loose tube design concept has won out. Whether it's OPGW or ADSS, if you're hanging it in the air and it's self-supporting, I'll throw that caveat in there. It probably is, and it certainly should be, loose tube design. In the loose tube design concept, the fibers can move in response to changes in elongation of the tube itself or the cable, because remember, they're going to end up working together. And those changes in elongation result from changes in temperature. OPGW is a metal cable, so it's going to change quite a lot in response to temperature changes alone, just from thermal expansion and contraction. Throw in addition to that ice and wind loading, and you're going to get even more elongation. The dielectric cables, plastic materials don't change as much in response to changes in temperature, but then it turns out they change even more in response to ice and wind loading. So in the loose tube design concept, what goes on is that you lay the fibers in the tube in a sinusoidal shape. So that means that the length of the fibers that you have inside the tube is slightly more than the length of the tube itself. So then what happens is if the tube gets elongated by tension or changes in temperature, the fibers are just going to begin to straighten out. And then when they get perfectly straight, they too start picking up whatever is causing that change in elongation. This difference, so the extra length of fiber relative to the tube is known as excess fiber length, or EFL is the common industry slang for it. And in general, you want EFL to be as high as you can get it. Higher is better, or as I like to say, no strain equals no problem. Strain is the point at which the fibers are picking up tension from the force that's elongating a tube. And that point is specifically called the zero fiber strain point, or the zero fiber strain margin. Now, I said EFL in general, higher is better. There are kind of some exceptions about that, but as a general rule, that's true. You can further increase it, EFL in a cable, by taking a tube and stranding it. And that's going to be important later when we look at certain OPGW design types. When you strand it, you have a lay length, and a lay length is the distance that it takes a tube, or another element for that matter, but it takes the tube to go a complete revolution about whatever is underneath, typically some center element. And it turns out that this puts a helix in the tube, and that increases the EFL by about 2.5%. In contrast, what you can get from the sinusoidal shape in the tube itself is only about 0.2%. So you get a factor of 10 difference here. Let's keep going. So you can make some inferences from what we just talked about. That is, first, if a tube is overfilled, then the fibers will not have the shape that they need to move freely, right? I can only stuff a certain number of fibers before I can't physically get the shape in them anymore. So that's not good. The other thing that comes into play, especially with OPGW, is how do you distinguish one fiber from another? There are 12 standard colors, but in OPGW, we're going to see later that you often have more than 12. So what do? Well, initially, what was done 30-ish years ago, 25, 30 years ago, was, well, we'll just try to add more colors. But that ran into a practical problem in the field, and that practical problem was that human beings were having a hard time distinguishing more than about 12 fibers under field conditions. So they dropped back to 12 standard colors, and then if there's more than that, you have one of two techniques that are used. One of them is called bundling, sometimes it's also called binder threads, where you take a group of 12 fibers and you wrap a color-coded thread around them to create a bundle. But that thread can also be called a binder thread. And so that makes a group of 12. Then you can repeat the 12 colors with a different color-coded thread, and now you're up to 24, and you can keep going. You can easily do up to 96 using that concept. Another technique that's used is to repeat the 12 colors but put a ring mark on them, a ring, sometimes called a band mark. But you have to be careful about that, because wouldn't those bundles binding a group of fibers actually restrict their movement? Well, it could, but today's manufacturing processes yield very consistent and well-coordinated EFL, so actually this bundling does work well. So the whole bundle moves in responses to change in elongation. I'm trying to avoid saying not just the individual fibers, because they're moving too, but they're moving as a whole unit as opposed to completely individual. All right. So we talked about fiber, we talked about the loose tube design concept. Now we're going to talk about the three types of OPGW that are used today. So there have been others over the years, but these three are the ones that have been left standing, so to speak. Why three? Well, because it's going to turn out that these have each design has trade-offs compared to the other two types. None of them is overwhelmingly superior to the other two types. So that leads to a situation where you need to look at balance the trade-offs to pick the one that's optimal for your application. So let's talk about each, and then we're going to go through and talk about the pros and cons, or advantages and disadvantages of each. But before we do that, real quick, you've got center tube designs. There are a couple flavors of that. Basically, there's a tube in the center of the cable, hence the name for it. I apologize, I've been fighting a cold, and I'm trying to suppress a cough. Here we go. The two flavors are just a plain stainless steel tube or a stainless steel tube with aluminum, which the aluminum can be added in a couple forms. We'll talk about that in a minute. So center tube designs. Next up is aluminum pipe type designs. So you have an aluminum pipe with plastic buffer tubes or plastic tubes in the center of that aluminum pipe. And then the third design type is the stranded design, back to a stainless steel tube, but it's been stranded around a wire, which could be aluminum clad steel or aluminum alloy, depending upon the design. So again, we'll talk about each design and the best version of that design. As I mentioned already, each design type has its own advantages and disadvantages. No one of them is categorically better than the other two. So first up, center tube designs, again, plain tube or a tube with aluminum. The advantage is it's a loose tube construction, but all of these are. But what we're going to see is that there's loose tube and then there's loose tube. In this type of cable, that EFL, the excess fiber length, your only source of that is inside the tube itself. Remember, I said if you strand a tube, you can get more. Here, the tube is in the center, so like almost by definition, it's not stranded. So all you've got is that sinusoidal shape in the tube itself. So no surprise, of these three design type, it's going to have the lowest zero fiber strain margin because it has the lowest amount of excess fiber length. Typically, that's going to be around 40 to 50% rated breaking strength. So relative to the other two, this is a significant disadvantage because your NESC Rule 250B, the traditional loading limits allow the tension under loaded conditions, regardless of the loading district, to be 60%. So you've potentially got a gap where the fibers could be experiencing some tension or strain, which could mean reduced reliability. That's going to be especially so if that fiber strain gets above about 0.2%. But these designs, the stainless steel tube provides great protection for the fibers. You get small diameters because these designs are mechanically and electrically very efficient. And because they're mechanically and electrically very efficient, no surprise that makes them very cost effective. So of the three types, they tend to be the cheapest. But they do have some other disadvantages in addition to the lowest zero fiber strain margin or lowest EFL, and that is that it's perceived to be more difficult to splice prep this stainless steel tube versus working with a plastic tube. The guys that do the splicing often work on other types of cable like ADSS or duct cable or even indoor cable. All of those use plastic tubes, so they have much more experience and knowledge of working with plastic tubes, and they're often a little bit intimidated working with the stainless steel tube. So it's perceived to be more difficult. I like to argue that that's a training issue. You need to be shown how to do it, but this is still kind of an objection that you often have to overcome. Relative to at least one of the other design types, you will find lower flexibility and higher susceptibility being deformed or crushed during pull-in. In particular, because of this, you often, not necessarily always, but often need to use an anti-rotation device, larger stringing blocks, and you'll have more pulling restrictions, like limits on the number of angles you can go through or the maximum length that you can pull. And finally, you have lower available fiber counts. Most suppliers can at least do 48, but about the highest or the highest I've seen to date has been 96. What's the best version of this? Well, I mentioned already, you've only got the sinusoidal shape that you can get in the tube. So you need to make the most of that, which means you need to kind of juice it up a little bit. But it turns out that the best you can get is about 0.4%. Remember, I said what's typical is about 0.25%. So you got to work it to get up to 0.4, and that's about the best you can do. If you're using the aluminum, there are two ways of doing it. You can take a stainless steel tube and put it into an aluminum pipe, or you can clad the stainless steel tube with aluminum. So it's NCAP's opinion, my opinion, that aluminum cladding is better to just putting in a pipe, excuse me, because you get an optical unit that acts as a single integrated unit. Whereas if you put a stainless steel tube in an aluminum pipe, you can get twisting or relative movement, and that can cause problems in the field, especially during splicing. When you're making that stainless steel tube, regardless of which type you're using it for, if you're using it with the aluminum or if it's just a plain steel tube, you need to have inline EFL control. So today's production equipment will ensure that you get that consistent and well coordinated EFL, as opposed to 90s technology, you got kind of loosey goosey EFL. Today, you should be able to get um, very precisely controlled and fully coordinated EFL, and that's good. Plus, when you're doing that, you should be having inline eddy current testing done to ensure that you get a 100% perfect tube. The gel that you use inside the tube, you can use standard gel, but you can also get gel that's been specifically formulated for use in laser welded stainless steel loose tubes. And that gel has a higher temperature limit, which is good because OPGW can get heated up from lightning strikes or from fault current. So that's good. Plus, the manufacturing process could put hydrogen inside the tube, could leave some inside the tube, which is not good. Fiber and hydrogen don't get along well. And the gel that's specifically formulated for these tubes has higher hydrogen scavenging capability. All fiber today has some ability to resist hydrogen, but this gets you, it's like some insurance, an extra degree of protection, so to speak. So we think that the gel specifically formulated for use in stainless steel tubes is better. And you can tell it because it has a slight color to it, whereas standard gel is perfectly clear. We talked before about using color-coded bundling threads, and those are good. And the splice techs like them because they can quickly group the fibers. But if you lose track of one of them, and it's easy to do, just a second of inattention, and you can lose track of a bundling thread, and then you're screwed, and you have to start over pretty much. So as a backup, if you use that ring marking I mentioned, then you've kind of got a little bit of belt and suspenders. So if you lose track of a bundling thread, you can use the ring marking, and at least you don't have to completely start over. So, we think this is best practice. And then in your wire fit, you want a good conservative fit like you see here. You don't want gaps. You also want to preform the wire a certain amount so that the wire stays intact when you cut the cable. It doesn't spring apart. These are important production parameters that you should watch. And best practices really means that these points really should be written into your specification. My recommendation to you. What I would do then is talk with the suppliers and get an idea of what's capable amongst all of them, and then write your specifications around what you learned from that. Naturally, I'd be happy to give you what I would recommend on these points, like things about lay length and fit, for example. Excuse me. Next up, aluminum pipe design. Again, loose tube construction, but again, not all loose tube is fully loose tube. Here you've improved it because you're stranding the tubes around something, and that gets you a boost in your EFL, which means a boost in your zero fiber strain margin. You can get up to about 50 to 60%. 60% is kind of about the best you can do because of the geometry inside these aluminum pipes. But it does mean that you can cover your NESC Rule 250B limit all the way up to 60%, potentially. So anyway, advantages, the loose tube, the splice techs like working with the plastic, so that's good. And this aluminum pipe has excellent electrical properties. Remember, one of the things you want is the ability to dissipate current, whether it's from a lightning strike or from a fault. This helps you do that very efficiently. But there still are some disadvantages to consider. First up, I do think that it's intuitively obvious to the casual observer that stainless steel loose tubes provide better protection than plastic tubes. my opinion. I'm a metal cables guy. I have that bias. Sorry. The aluminum pipe is relatively inflexible and susceptible to being deformed or crushed during pull-in particular. That's not good. Because of this, this cable type always requires an anti-rotation device. Always, always, always. It also generally requires larger pulling blocks or stringing blocks, and you have more pulling restrictions, the number of angles that you can go through, the distance you can go through, and so on. The aluminum pipe in some environments can corrode. That is a problem here in parts of Texas where I'm at. Large birds of prey and vultures uh, sit on the cable and they do their number two, and it's very acidic and it corrodes away this aluminum pipe and bad things happen optically. This cable type also tends to be the most expensive because you've got extra manufacturing steps. You've got to make the tubes and then you got to put them into a core, and then you got to put them inside of pipe. That means more cost. So it tends to be more expensive, all else being equal. Best practices for this type of design, first up is what plastic do you use for these plastic tubes? There are lots of different plastics out there. We think PVT is the best to use. It balances temperature performance, which is important for OPGW because it can heat up a lot, but it can also be really cold, when it's winter out. It's abrasion resistant, good crush performance, good material to use, our opinion. When you're making this core, you should use reverse oscillating lay. That's also sometimes called SZ stranding with the conservative lay length. That helps facilitate the splice prep process. It's good to protect these plastic tubes with something, right? They should be protected from heat in particular. So a thermal barrier around them is good. And then if water gets inside, eventually bad things would happen. But a water absorbing medium does help provide protection. And it also helps ensure that if that happens, that ends up being a planned replacement as opposed to something happening at dark 30 on a cold winter day and everybody has a bad day because it's a crisis. How do you make this aluminum pipe? Well, we think an extruded aluminum pipe is better than welding, right? Because with extrusion, it's seamless. With welding, you have the potential for weld cracks or maybe over welding and under welding could both be problems, whereas extrusion kind of takes those out of the question, or out of the picture rather. Again, be conservative with your wire lay length and the preform of those wires and the fit. Last up is the fully stranded design. Advantages of the three design types: it has the highest zero fiber strain margin. You can easily get more than 80% rated breaking strength. You don't even have to try hard. That means that you can cover, in addition to the traditional NESC limits, you can cover concurrent ice and wind or extreme ice conditions under NESC 250 C and D. I think the stainless steel tubes provide good protection. This looks and handles more like a conventional overhead cable. It's like you've taken out some wires and replaced them with tubes. That makes it more flexible and crush resistant, excuse me. Because of this, you generally do not have to use an anti-rotation device for them. Some suppliers will require them, but many do not, including us. That allows you to go longer pulls through more angles and may yield fewer splice points, which save money if you're eliminating splice points. But unfortunately, they still do have some disadvantages. They're not as mechanically and electrically efficient as the other two. This is because when you look at this cross section, you see you end up with these gaps, and that's, kind of wasted space. Hate to say it, but it's true. And you're back to having this problem that some splice techs don't like working with the stainless steel loose tube. Best version of this cable, Well, one thing that you need to do is you got to watch the size of the tubes relative to the wires around them. You want to slightly undersize them so that you get kind of a bridge effect. So any kind of a crushing force on this cable, the entire cable has to be giving before the stainless steel tube itself sees any of that force. So you could think of it as kind of strain margin for tubes, crushing strain margin for tubes is one way of thinking about it. Uh, After that, a lot of the same things that you saw with the center tube design. You want the inline EFL control and eddy current testing. You want the gel formulated specifically for use in stainless steel loose tubes. You want to color code your bundling threads and your ring marking. Use both together to facilitate the splice prep. And you still want to be conservative with your wire lay length and your preform so that you get a good fit, like you see in the picture here. So let's look at design parameters. For any OPGW, regardless of the design type, the three most important parameters are going to be your fiber count, the maximum diameter, and the fault current capacity. Now, me as a cable designer, I would like to say that, well, diameter, you should let the diameter be whatever the diameter is. But in the real world, that just runs up into some practical problems. And the truth is that utilities often have a maximum diameter requirement, and that becomes an important factor in the cable design, critical factor in the cable design. These factors interplay with each other and they work against each other. They create significant trade-offs because on the diameter issue, you always want it small. Nobody goes to an OPGW project and says, I want the largest diameter possible. No, it's always the opposite. You want the lowest diameter that you can get so that you're trying to put less loading on your structure or minimize your loading on your structure. But um, so you want a small diameter, but you may need high fault current. But high fault current means more metal, and more metal means a larger diameter. And then cost enters as a trade-off also, right? The more metal, the more cost. But of course, you're trying to keep costs down. So they work against each other. That fiber count, give you some insight what we see. 48 is still by far the most widely used fiber count. We do see a lot of 72 and 96, good quantity of 144. We don't see much of anything below that. Below 48, I should say. What about the fiber count per tube? 24 and 48 are the most common by far, and this leads to tube counts typically of 2 if you're using 24 fibers per tube, or 1 if you're using 48. Again, a 72 fiber or a 96 fiber center tube, it's going to be a 1 at 72 or 96, but I'm just saying these are the most common. And I want you to point out that you need to contrast this with what you see with dielectric cables, because in dielectric cables, 12 and 24 are still the most common. So you end up typically with 4 tubes or more in a cable. And so if you're splicing OPGW to a dielectric cable, and you often are at the substations, um, this requires some reorganization in the enclosure. So, and whoever's keeping track of what fibers are doing what also has to pay attention to that when you're recording the network layout. Now, each tube size has a maximum fiber count, because go back to when I was talking about the loose tubes, you got to get that sinusoidal shape in it. So you have to have a certain amount of space to do that in. So a good design is going to maximize that zero fiber strain margin, which is to say maximize the EFL given the available space. And as a consequence of that, so conversely, it's going to minimize the fiber strain at that maximum rated design tension. So that's the highest tension that you're using for the cable. Ideally, you would like that to be 0, but as we talked about before, with some of the designs, like the center tube designs, you often can't physically do that. So you do want to minimize it, but you'd like it to be 0, but you can't. I'm going to give you an important tip here that just occurred to me when I got to this slide. A poor design of a cable, specifically a poor optical unit design, will show up as low EFL, or which could be a consequence of low EFL, or overfilled tubes, which is really to say low EFL or whatever. In any case, poor optical unit design is going to show up as low zero fiber strain margin or high strain at MRDT. A lot of cable suppliers, though, won't show you this. You have to ask for it. If you ask for it, they should be able to provide you and should be willing to provide you this information, and then you can make an assessment. You'll recall that I mentioned it kind of in passing that you'd like to keep the strain. If you're going to have strain, try to keep it less than 0.2%. If you're going to allow it. Ideally, you'd like to have none. If you're forced to have some, try to keep it definitely below 0.2%. Your tube size is a function of your, what's going on in your cable. So if the design type itself affects that. For now, that's enough said about that. On the cable diameter, as I've already said, you want it to be small, but then you're limiting your fiber count and your fault current. Typical diameters that we see are 0.364 to 0.767. There are a little bit smaller ones. There are some bigger ones, but this is typical. And then of this, the most common is 0.465 to 646. You can go larger, you can add more layers, but you're increasing cost. As the diameter goes up, you're going to know this. You increase your structural loading, but you also increase the cable cost. You also shorten the reel lengths, the maximum reel length that can be produced, and that can mean more setups and more splices, and that can even increase hardware cost as well. So, two topics to close out, and I got to hit it fast because I'm looking at the time running out. First, fault current. So fault current, you have to come up, the utility has to come up with a required capacity, and then the cable manufacturer has to come up with a cable design and a cable rating that meets that capacity. And I will note, this is a real brief overview. We do have a webinar that does a deep dive on this topic. So today I can only hit the highlights. So this is what that looks like. The utility side is creating a requirement, and it has these elements to it. And then the cable supplier has to take that requirement and turn it into an actual rating for a cable. The important point for you guys on the utilities side is that ultimately this fault current requirement is a function of your design philosophy. That's what you would see when you talk about the details of what goes into this calculation. So how much current am I allowing? Obviously, the higher this rating will be, then you've got to have more metal in the cable and all the, the ripple effect of that. Your duration of the fault is a factor, and that too is going to potentially increase or decrease this number. Basically, it's part of the calculation. So ultimately, what you find when you do deep dive into these is it boils down to how much risk is acceptable to you and your utility, if we were to talk about those in detail. And then the cable manufacturer side, when you look into this in detail, what you find is that it's important for you to make sure that your suppliers are all using the same parameters in their calculation, and in particular, the same methodology. These are particularly critical variables, the initial cable temperature and the final cable temperature, but the methodology is important to do too, and you need to make sure that everybody's using the same rules. That allows you to compare the rating of one supplier versus another supplier, and more importantly, it allows you to make sure that the supplier rating meets what you determined you need. So some people will say, yeah, but can't you just say we're using 3/8 inch EHS? Let's just make it like that and make it the same. And there are two problems with that. One is that you can't find data on it. That's a very vague requirement. Go look at any conductor manual, and you flip to the page for the steel cables or the ACS cables, and you won't find fault current capacities listed there. So then you have to do some guessing as to what those cables capacity are. And if you do that, what you'll find is that those ratings are very low for today's grid. Why? Because many of these conventional cables were picked to be used as shield or ground wires 100 years ago, and the power grid was very different back then. So next up, or like really the last topic, is lightning performance. Lightning performance 2, we have a webinar with a deep dive on this. And but for now, what I'll say is uh, we believe that if you design well for your fault current, you're going to get good lightning performance too. So we don't think you need to do anything special. It turns out there's no agreed upon guidelines for lightning designs anyway. But we can share our observations and experience about it. So the observations, size of the wire is important. The material that you're using is important. The wire count is important. And the overall cable diameter is important as well. Again, don't have the time today to go into these in detail. We do have a separate webinar where I go into nauseating detail about all of these things. In addition, low footing resistance correlates with low incidence of lightning damage. And that's because strikes are more likely to hit at or near a structure where the cable has added protection when the footing resistance is low. Now, you're probably wondering, well, what about the design type itself? Is that a factor? And the answer there is, well, yeah, it is. You need to view this in light of the other factors, the trade-offs and things like that we discussed. But nevertheless, there are some rough guidelines I can share are that those center tube designs do good. I mean, they're in use today commonly. They wouldn't be if their lightning performance was crappy. So they at least meet the standard of good. But I do think that the aluminum pipe designs are a little bit better, all else being equal. And all else being equal, I think the stranded stainless steel loose tubes are the designs are the best. Very rough guidelines on this. Okay. All right. And I just want to close with we on our website, we do have a thing that we call the configurator, the advanced cable engineering system. That can help walk you through the process of determining an optimal design based upon your project specifications or requirements. It'll also help you select the accessories that you need for a cable. Just check it out. And that's all for today. So a little bit long on time, but we'll open it up now for questions. And while you're thinking about your questions, you can just put them in chat. I will mention that thank you for attending today. You will receive a follow-up email. That email is going to include a link. If you want to get the continuing education credits that I talked about, click on the link. It'll take you to where you can do a test. You got to pass the test. It's not a terribly hard test, in my opinion. Take the test, pass with 70%, and we'll get you your credits. There'll also be a link for a survey. We ask that you do give me some feedback, and I'm very open to suggestions for any kind of improvement, other topics, how I can make this better. I'm always open to ideas. So, do we have any questions? Not seeing any. Still no questions? You're a quiet group. That tells me I either did a really great job or I did a really lousy job. Okay, we'll give it maybe another 1 minute. If I don't have any questions, I'll just say thank you for your attendance and appreciate your time and attention today. And thanks for coming. Oh, well, I do have a thank you. Very informative. Thank you, Jeff Bell. Appreciate that. Have some other positive comments. I'll stay on for a few minutes. If you have questions, throw them in the chat. Otherwise, enjoy the rest of your day and have a great, the weekend's coming up. Enjoy your weekend. Oh, let's see. I do have a question here. For a replacement project, how can we select the best OPGW? The oh, that's a good question. What I find often is when people are doing replacement projects, it depends like what they're replacing. If you're replacing an OPGW that has had problems and has maybe failed prematurely, that's a little bit